Our universe is a strange place. Modern science helps us understand just a little bit more of what is going on around us, but many things still remain unsolved. Black holes are one of the scariest and extreme interstellar objects. Today we're going to go deep into the secrets of these mysterious universal anomalies. In this video, we'll cover the following questions. What is a black hole? How is one born? What is it made of? What happens if you fall in one? What happens if we replace the sun with one? And how does one die? What is a black hole? A black hole is a region in space where the gravity is so strong that it pulls everything towards it. Even light cannot escape it, rendering it invisible. A black hole occurs when too much matter is crushed into an infinitely dense place. The density of the matter is so great that it completely warps space-time, creating a hole of sorts, with a central point that is hypothesized to be infinitely dense, called the singularity. Humanity still does not understand what occurs at the center of a black hole. Contrary to popular belief, black holes don't actually suck up anything. It's more that the matter falls to the center of it and gets attracted by its gravitational field. Also, black holes come in different sizes. At the center of our galaxy, the Milky Way, there's Sagittarius A, and you can also have a smaller black hole. The smaller black holes are actually deadlier than the bigger ones. And this is because the small ones have very extreme gravitational tidal fields. Let's summarize what we've just seen. A black hole is a region in space where objects fall into them. They have different sizes, such as the ones at the center of galaxies, and they have an infinitely dense point called the singularity. So, where do they come from? To answer that, you need to know a little bit about stars. After several billions of years, a star will begin to die. A star is in a constant fight between the crushing force of gravity and the pushing force created by the giant quantity of energy that is generated from the nuclear fusion inside the nucleus of the star. This phenomenon is known as nucleosynthesis, which is, according to the Merriam-Webster, the production of a chemical element from simpler nuclei, as of hydrogen, especially in a star. The star will continue to fuse elements into heavier elements and therefore fight back the crushing force of gravity. In its lifetime, the star will fuse hydrogen into heavier elements. Smaller stars can fuse for much longer than supermassive stars because the core has less pressure and is cooler. For much bigger stars, the extreme heat and pressure allows them to fuse up to much heavier elements like silicon and iron. That's when the star dies, because it can't fuse iron into anything heavier. No fusion means no fighting back gravity, and that's when gravity wins and causes the star to collapse. All the matter that made the star suddenly starts falling to the core at an incredibly fast speed, where new matter is created. The matter then gets pushed outwards in an explosion called a supernova. The remnants of a massive star is either a neutron star or a black hole. Two incredibly extreme, unstable, and logic-defying structures. For smaller stars, dwarf stars, who don't have enough energy to explode into a supernova, a much more stable, cooler, and dense object is created, a white dwarf, which lives an incredibly long life. To summarize, when a star no longer fuses elements, or starts trying to fuse iron, gravity wins over fusion, which causes all of the matter that made up the star to come hurtling to the center of it, creating a supernova. The remnant of a supernova for a massive star is either a black hole or a neutron star, and for a smaller star, it's usually a white dwarf. In 2019, we captured the first ever image of a black hole. It doesn't really look like much, but in this section of the video, I'll explain what is going on in this picture and the anatomy of the black hole. So this blurry orange layer around the black hole is an accretion disk made from two things: matter orbiting it at an incredibly high speed and in incredibly high temperatures, and the photon sphere. This area has a big gravitational pull. It's so big, in fact, that the light, or the photons, are forced to travel in orbits around the black hole. The unit of measurement that we're going to be using to describe the different areas of the black hole is called the Schwarzschild radius. According to Britannica, the Schwarzschild radius, also called the gravitational radius, the radius below which the gravitational attraction between the particles of a body must cause it to undergo irreversible gravitational collapse. This phenomenon is thought to be the final fate of more massive stars. On the outermost layer is matter, but if it gets any closer than 3 Schwarzschild radii, it falls into the black hole. Since light is massless, it can orbit closer to the black hole at about 2.6 Schwarzschild radii. If you were to stand in the photon sphere, you would be able to see the back of your head because the light orbiting the black hole would diverge and come back to your eyes. It's very logic defying. The light is technically going straight, but since space-time is curved, the light appears to be curved. The dark spot on the image can be interpreted as the event horizon, where no matter escapes the black hole, hence the name black hole. The dark part in the image is actually every single side of the event horizon, because we can see all of its sides due to the photon sphere. So we have an accretion disk, more or less the orange part, which constitutes the ergosphere, and we have the event horizon, where nothing, not even light, can escape. Past the event horizon, the center of the black hole, is the singularity, an infinitely dense point in space. Modern science still can't explain what happens here, as aforementioned in the previous section of the video. So, what we've just learned is that the black hole can be static or rotating. The orange part of the black hole, also known as the accretion disk or ergosphere, is made out of the photon sphere, which is light in steady orbits, or matter, that is at an incredibly high speed and temperature. The black region is the shadow of the event horizon, which is seen on every single side. At the center of the black hole is the singularity, the infinitely dense point. We use the Schwarzschild radius to measure the black hole. Now, what happens when you fall into a black hole? That's a crazy thought, but this is what we know so far. Now, let's say you're in a spacecraft with your crewmates approaching Sagittarius A, a supermassive black hole, and you decide to jump out of your spacecraft towards the event horizon. From your point of view, you would keep falling and the darkness would slowly envelop you. Your only view of the outside would be a small light. You would slowly descend to the singularity and feel the crushing force of gravity. Every direction you move only brings you closer to the singularity. As you fall, your crewmates would see you get smaller and smaller until you freeze at a certain distance and become redshifted. That's when the light you emit before fading out of existence turns toward the red side of the electromagnetic spectrum. Then you fade out of existence. So, you're falling towards the event horizon of a smaller black hole, much more lethal than a supermassive black hole such as Sagittarius A at the center of the Milky Way. Since your feet are farther than your head, the gravitational pull on them is drastically larger. This results in you turning into a long, hot spaghetti of atoms. You become spaghettified as you descend to the singularity. This is much worse in smaller black holes than larger ones. So, that's cool and all, but what if you replace the sun with a black hole? I'm going to let you pause the video for a second so you can write down your hypothesis. Alright, so I've just created a simulation of the solar system, and we're about to change the sun into a black hole and see what really changes around here, alright? So, what I mean by changing it into a black hole is that I'm gonna change its radius, and we're gonna see what happens real quick. If we were to change the radius of the sun to something a lot smaller, basically what we're doing is we're taking all the matter that made the sun and we're pushing it into an infinitely dense place. And if you remember in the video, I was actually talking about this earlier, and that's pretty much the definition of a singularity. So we're effectively creating a black hole by squeezing the matter of the sun into a very dense ball of hydrogen and all those other constituents. As you can see, the surface gravity is rapidly becoming greater and greater as we diminish the radius. So our radius is about 2.8 kilometers. Earlier is of 1 kilometer. But yeah, this is our sun, and that doesn't look too good, I'm gonna be honest. Now let's see if your guys' hypothesis was correct. So I'm gonna unpause the simulation and we're gonna see what happens. To make sure that nothing changes, because right now I don't see any change, I'm going to actually speed up the simulation. So now we're going at 1,000 days per second, and the orbits are pretty much the same. Now, what we see here is the effect of gravity is the same because the sun still has the same mass, right? It's just a lot more dense. So in the end, the mass is the same, and so the gravitational field, the gravitational pull exerted on all the other objects are basically the same. So same orbits, same everything, nothing's changed. Of course, you don't have a sun anymore, so let's go check out Earth, how cold it is because there's no sun. Yeah, it's effectively a giant ball of ice. So yeah, we're not getting sucked into the black hole because that's not how things work. But, you know, same orbits, we're just frozen to death, which is quite grim if you think about it. In this final section, we'll discuss the death of a black hole. Black holes are some of the oldest things in the universe. The ones we observe are usually the remnants of the very first stars. Black holes evaporate due to a thing called Hawking radiation. Beware, the following section talks about quantum physics. So if you're not familiar with it, it's perfectly fine. I'll sum it up after this tangent. Alright, this here is the standard model of particle physics. It's like the periodic table, except it contains everything, well, almost everything, that makes up the universe. To understand Hawking radiation, we need to take a look at these things here. These are quarks. They make up hadrons, such as neutrons and protons, that you've surely heard a lot about in chemistry class. These guys are held together by one of the fundamental forces of the universe, the strong nuclear force. Basically, the gluon, the mediator of the strong force, makes the quark transfer color charge as shown in this diagram. The gluons hold the quarks together and make up the hadrons, like neutrons and protons, and these guys make up atoms, which are elements, make up molecules, which make up matter, which makes up most of the visible universe. Now, these quarks also have anti-quark versions, which make up antimatter. In the vacuum of space, there is a constant annihilation of quark-anti-quark pairs. Here is a Feynman diagram that illustrates this. Alright, we are now exiting the quantum physics section. Basically, in the void of space, there are quarks and anti-quarks popping in and out of existence. When a pair gets created inside of the event horizon, one quark goes into the black hole and the other one goes back into space, creating matter and making the black hole lose energy. The black hole slowly absorbs more and more quarks and loses exponentially matter and diminishes in size. Worry not, in your lifetime you will probably never witness a black hole evaporation. Heck, they take so long to evaporate that the biggest black holes might get destroyed in about a Google years. That's a very long time. When a black hole fully evaporates, we think it will create a massive explosion. So, what we've just seen is that in the void of space, there isn't actually no matter, there's actually quark-anti-quark pair annihilations. And that's what's responsible for Hawking radiation when one of the quarks spawns inside of the black hole. And that's what causes the black hole to lose energy and evaporate. Anyways, I hope you guys learned a thing or two from this video. Don't forget to leave a like or a dislike if you enjoyed the video or if you didn't. And please consider subscribing, it means a lot to me. I really enjoyed making this video, and it's one of its kind truly, because I've never tried this big of a feat in video editing, nor used this many software in order to create something. I'd like to thank all the sources that I used in order to create this video. Thank you to Universe Sandbox for the 3-dimensional simulations, and most importantly, I'd like to thank you, the viewer, for enabling me to create this content. I will be seeing you guys next time in the next video.